Forrónak és az nem menekült, csak 4 évben áll. Én csak kérdeztem, hogy abban élesen egy ilyen légkondis felelős.
So let me pretend where we yesterday. So remember, so we introduced this van der Korput inequality. So this is a very general principle, very important. Got it here and other places. So this is in fact, surveys are number distribution estimates are exponential. Some estimates, but these are something that is very important. It becomes very important in linear harmonic analysis and in combinatorics. And what is important, so I like to, so let me also state when think about this. So it is multilinear problems arising in ergodic theory. So this principle, this is some replacement of TT star argument, in fact, so the fact that here we translate by H, and then we can, for instance, in the polynomial setting, we can go, we can decrease the degree of polynomial as we have seen in this theorem here. For instance, here, if we verify this condition, you see that a polynomial of degree, let's say D, becomes a polynomial of degree D minus 1. So this is like applying TT star argument for this aberration operator. Right? This has the van der Korput has is much better adjusted, not only to operator, but multilinear operator and any other context. So that's a very powerful thing. So it's another thing of another way of thinking about van der Korput. This is some principle to detect orthogonalities and this condition, but this is not maybe not orthogonality between these vectors, but some kind of asymptotic orthogonality because of this condition. You have this, then this is some kind of almost orthogonality. So that's not very far, from some ideas that arise that are important in harmonic analysis. Therefore, I like to think that from the principle perspective, harmonic analysis are important in this thing. Explored for many years by science operators. Okay, so here we proved this for this. So we started. Remember, we proved the variant of extension of von Neumann ergodic theorem for total ergodic systems. For total ergodic systems, we have this convergence to this constant, which is an integral. So in other words, we know that this polynomial time average is converged to space average to norm. This is also true for pointwise convergence almost everywhere for functions of these spaces, but the proof is much harder, involves a lot of technology from number theory or circle method. And so as a corollary for total ergodic systems, we derived this nice variant of one recurrence theorem for polynomial orbits. And now, if we want to, use this to, if we want to derive combinatorial applications, for instance, the Furstenberg-Sarkozy theorem, which says that we have subset of integers with positive upper density, then it contains two integers whose difference is, for instance, a perfect square. Then we would like to have this, but for all microprojective systems. And so that's an important thing. And so Marco, yesterday you asked about this, what happened if you take two different sets here. And we asked in the general manipulative transformation. And so next in the next lecture, you will see that this is in fact certain concept of weak mixing. So we will discuss this. And you will see how we will see how efficient it is in one of the context of rough theorem and summarized theorem also. So weak mixing is a very important class of measure preserving systems where summarized theorem can be proved by direct application of van der Korp in a so we will see that hopefully today. And so this is Furstenberg Sarkozy or Sarkozy Furstenberg. Sarkozy proved this for squares by using circle method purely from analytic number theory, but Furstenberg then was interested in and he derived this for polynomials by using ergodic methods. And our aim will be to show how to use these ergodic methods to derive this result set with positive upper density and any polynomial with coefficients with zero constant term. Then under this setting, we can find two integers in E whose difference is exactly this polynomial. So that's Furstenberg, and this kind of results can be derived from this ergodic setting once we have this kind of type of recurrence theorems. And so here we deduce this. So we know that this result, as I mentioned yesterday, holds for totally ergodic systems. So therefore, we know the strategy now is to build two spaces. If we know that some phenomenon holds for certain class of measure preserving systems, so we consider a closed subset of a Hilbert space for which these properties we know that they hold, and then we want to understand what happens in the orthogonal component. And this is what we do here. This is why we introduce the composition rational spectrum. So this is this closure of two functions which are whose K power of Kaplan operator, functions which are invariant under the K power of Kaplan operator. And the other, the totally ergodic component, so which has this form for all K, we require that this converge along these orbits to 0. And it turns out that these two sets are orthogonal and they direct sum spans the entire Hilbert space. And now, so we can use now this to, so we discussed this proof yesterday, and now we can use this result to verify polynomial Poincaré recurrence theorem. Which is the result of this form, but now for all measure preserving systems. So we know that this holds for totally ergodic system. And in order to see the proof, so we fix a measurable set and we consider its characteristic function, and we split this into this rational spectrum component and totally ergodic component. And we know that those two functions are orthogonal to each other, and rational component, so let me remind this part, contains constant functions. So therefore it's orthogonal to G1 is orthogonal to G. So therefore by the Cauchy-Schwarz, we start with this, we add G and subtract. So F minus G is orthogonal to F, and so therefore we have this. No, sorry. Okay, so here this is this decomposition, and and of course X orthogonal to G. Therefore, this can by linearity of the scalar product. We have normal F, but normal F. So this is the square of this, And now this, because of this identity, is equal to this, and G is orthogonal to 1, so therefore we have this. Okay, so we have this lower bound for this expression. And now, so because now we can find now f is taken from rational component, which is the closure of this. Therefore, by density, by the fact that it's closed, then we can find H in this set with the property that this identity holds for a certain K, and H is close to F with this error. As I said, because this is defined as a closure. And from this, it follows that we can replace F with H here, and we get this lower bound for this quantity. Okay. So this is what we do now. Here, it's important that the constant term is 0. So this is the important place where we will use the fact that zero term of this polynomial is 0. This assumption is needed. And we consider this polynomial p, k, n, and modulo k. So and we see and of course we have this because this holds for, we remember that this identity holds for tk, so therefore it will also for whole multiple of k for iterating, and q of n's. So this is the definition. So therefore, if we have 0 term, then we see that this is divisible by k. So therefore we have this, and for all integers in fact. And now, by the van der Korpel lemma, we can deduce that this limit is 0 because now we have this this identity. And we have, of course, we have this by words, and the fact that G is taken from this totally ergodic component. Okay, so therefore this converges. This converges to this converges to 0 by the fact that G is the totality. And so, and now we can finish the proof because we want to understand this expression, the limit of this expression. So now this is interpreted as this, the average, and here we can put characteristic functions, okay, and characteristic functions composed with this orbit. And now we decompose this characteristic function according to this splitting here, and this function, additional function, h from this set, and we have the following. Now we see that this part is small because everything is in L2 and this is close. These two elements are close in L2 norm. And this guy converges to 0. So therefore we have that and this is the expression that we want to estimate. We understand we have some bound point 0 for this. And this is smaller than epsilon over 2, smaller than epsilon over 2, or the sum can be made, in fact, smaller than epsilon over 2. And so if we combine this, so the lower bound that we derive here, we see that this is measure A squared minus epsilon. And this completes the proof of this of the polynomial quantum recurrence theorem, and that's how we get it. And this is, as I said, so formally we can think that this is ergodic variant of Sarkozy here of this result in additive combinatorics. And let me now explain why, because of the first inverse correspondence principle, which can be formulated as this nice result. Says that it says that if we have a subset of integers, then there exists a measure preserving system, a probabilistic measure preserving system, and a measurable set. And two properties are important here in the conclusion. So the measure of A of this new set is exactly the upper density of E. So this is equal to precisely this value. And moreover, for every finite subset of integers, we have that the measure of this event is dominated by the measure. So we can think that this density is some kind of measure of the set of integers. So it's dominated by the measure of this event on the set of integers, where S is a shift operator of the set of integers. So that's what we have. So in other words, you see that this. So if you are familiar with Calderon transference principle in pointwise convergence, then the set of integers is also universal for all quantitative bounds. And so therefore quantitative bounds like maximal inequalities, for instance, for the it's sufficient, if we are interested in maximal estimates for ergodic operators, so we can transfer everything to the set of integers, and the norm of any maximal function on arbitrary dynamical system is controlled by the norm of the corresponding one on the set of integers. And see here, there is some similar result that the set of integers in this sense dominates any other measure preserving systems. And here, in this context, the measure, the counting measure is not good because this is infinite measure, but it can be replaced with this upper density. Okay, so now we have. So here is a proof, and so this is what I told you last time. Here it's better, to make with the subset of integers, which can be identified with the counter set, because, like, for instance, in this simple exercise from set here, when we want to prove that the set of all subsets of integers has cardinality continuum, then this is what we do: we establish bijection between the set of infinite binary sequences and the set of all subsets of integers. And this bijection, for every subset of integers, we associate its characteristic function. It takes only variables 0, 1, and we are done. This is the bijection, and this is what establishes this one-to-one correspondence between these two sets. So therefore, instead of working with set of integers itself with counting measure, which is not good for the because it's a sigma finite measure, it's not good for the Poincaré recurrence theorem. It's much better, to work with the set, the counter set, which corresponds to the subset of all integers. And the counter set has this nice property here. So let's go. So here, so this is what I mean by counter set, and this is a compact set. We have a shift operator on this set, and so now, in order to construct this measure here, so this would be a consequence of Van Allen theorem, in fact, and so the properties of the and the definition of the upper density. The upper density. So here we have the definition of the upper density. So therefore, if this is lim sub, so this means that this is lim for certain subsequence of integers. And now if we introduce this set here and we construct omega n to be an element of X with this property that's equal 1 whenever n is in this set E and 0 whenever n is outside, then we can define this sequence for every j. This is the average of the characteristic function of the n iteration of omega. So in other words, So we start, so we consider all sequences that starts from the n digit of omega, and j. This is the element. This is the j element from this sequence that for which this quantity has this limit. And now, so this is what we do. We can see that we can define. We can see that a simple calculation shows that this is equal precisely mu j. If we define this limit this way, then we see that mu j of a, this is precisely equal to this, because of our definition of a in the contour set. So we consider all sequences that starts from 1. And now, so this is what we do now. So by we use Riesz representation theorem. So in other words, this defines linear functional, which is bounded, and in fact, this sequence of linear functionals is uniformly bounded. So therefore, we can use Banach-Haloglu theorem. So therefore, this is by Banach-Haloglu, the set of those elements by Banach-Haloglu theorem has a subsequence, and therefore, consequently, there's a linear functional in the dual with the property that for certain subsequence, this sequence of linear functionals converges. By Riesz representation theorem, therefore, we need to have a Borel measure, probability measure with this property. In fact, this is what we are looking for. So this verifies, this measure is equal to the density of this set, and that's the first property that we need. In order to verify the other property, we use Stone-Weishaupt theorem, because we have to show that this measure is measure preserving in the following sense for this shift operator on the contour set. And it's obviously to consider linear combination of indicator functions of cylinders. Cylinders are sets that depend on the infinitely many axes. And these functions are dense because the characteristic function on the contour set that depends on the cylinders, characteristic function of cylinders are continuous functions. So linear combinations are continuous, and this is how we can verify this. By the way, here you see that because of this topology on the contour set, so in fact, this shows that this argument shows that this is the proof of Riesz representation theorem on the contour set. By the way, in this setting, Riesz representation theorem is very simple. I mean, Riesz representation is the following: that for every linear function, one can be represented as an integral corresponding to certain random measure. Then on contour set, it's very simple. So that's in fact, this is what we are discussing here, is the proof plus Stone-Weishaupt theorem. And now, so we can see, and here we have to verify this condition here, and this can be done by verifying this on cylinders, on cylinders we only verify the fact that this is measured preserved in the system. And now we have to prove this, that the density of this event dominates the measure of this event corresponding to our set A. Remember, the set A is a set of all a sequence that starts with 1. The first digit is 1. So therefore, T inverse T minus NA, this is the set of all elements whose nth digit is 1. And for every finite subset here, so we start with this, then this by the definition instead of this for all n in F. And now we see that if we translate omega, this is this characteristic function of set A, translated by n. So this means that n plus n must belong to E, sorry, for all n in F. but this means that the intersection of this contains and elements from here. And now, so we see that this is precisely equal to this average. And here this hash means that this is the so, and this is precisely, if we pass with J with the limit, then it's precisely. So that's how we get this proof. So, and this is how we obtain Furstenberg correspondence principle, and now we can use this plus the Poincaré recurrence theorem to deduce Sarkozy-Furstenberg, which is the result of this form. And in order to do this, we first we fix our polynomial. By Furstenberg correspondence principle, there exists space and probabilistic space, invertible measure preserving transformation. In fact, because this proof shows that T can be even taken inverted. We have this identity, and we know that because our set in question, this setting Furstenberg-Sarkozy has positive upper density, so therefore the measure of A is positive. And moreover, we have also this, and now we apply here, you see that, let me go back to Furstenberg correspondence principle. So we will apply this with F, which is equal N, comma P of N. Okay, this will be the set. So here, therefore, the second part of the Furstenberg correspondence principle says that this is dominated by the density of this, where S is the sheaf operator. And now by Poincaré, we know that we have lower bound for this, which is of this form. And on the other hand, we know that this is positive because of this part. And also now epsilon is arbitrary, so we can take 1/2 of the square of this one, the measure of A, which is also positive. So therefore we obtain that this is positive, but if density is positive, then it means that this set in particular is non-empty, and this proves that there are X and Y in the whose difference is P of N, and that's the proof of the Sarkozy Furstenberg. So and so here you see that so this is what, so there are two components of this proof. So Furstenberg correspondence principle, which is an important tool to translate these problems from additive combinatorics to the ergodic setting. And then we have recurrence theorem, and this is where we have to prove something, by using this ergodic methods. We can check. So therefore, everything from additive combinatorics is reduced, to the ergodic setting, and now we can use this Hilbert space techniques mainly to and some other measure theoretical tools to deduce this to establish recurrence theorem. So therefore, recurrence theorem can be thought as an ergodical interpretation of this results from additive combinatorics. As long as we have some kinds of recurrence theorems, and then apply the Furstenberg correspondence principle, they can translate it to the setting. So and this is so I wanted to present this in the context of Sarkozy because this is quite clear, and everything is very elegant. But now let's talk about Roth theorem. So here, this is the so we will talk about now. We want to establish this for K equal to. So this will be our aim. Now by using ergodic methods. So let me. Okay, so this is what we already discussed. Here we have van der Kolk. So let me see what we. Okay. Now I just wanted to. Okay, so we go. So we can start. So we are familiar with van der Kolk. This will be important ingredient in establishing graph. So, but there are other things which are important. In first thing will be the concept of weak mixing system. So here you see that we have weak mixing means that the measure preserving system is weak mixing if this falls for all measure of the set. So this is here you see this is the definition. This is what you asked yesterday, Marco. And so it's a very important concept here. And with mixing, one can show that implies total ergodicity, which is not it's not difficult, but it's also not straightforward. And then total ergodicity, of course, implies ergodicity. Total ergodicity means that every n power of t must be ergodic. So that's the hierarchy. And there is also another concept, strong mixing, which means which implies this. Strong mixing means that the limit of this guy without average converges to this product. So this is some kind of asymptotic independence, understood in a very strong sense. But here we can think that this is also some kind of asymptotic independence, but understood in a very weak sense, taken in average. Okay. Here is important that we have this absolute value inside this average. And in fact, we can put any power here. If we put any power here, then this is also true. So this condition with all powers, this is this if converges to 0, then this is equivalent to weak mixing. And we will use this, with power 2 at some point. Or equivalently by some density argument, we can deduce that for all square integrable function, we have this, where I will use this convention that this denotes the average of that. And of course, here so here this is the simple property, implication that weak mixing implies ergodicity. And in order to see this, so we just use this observation that we consider T invariant set. Then we have obviously this, okay, and this is equal to this average, because of this identity. And if we pass to the limit by this condition, then this converges to mu r squared. So therefore, in probabilistic work from now on, with all dynamical systems, all measure preserving systems are probability, and they correspond to probability measures. So therefore, this by weak mixing converges to this. So therefore, measure of S either 0 or 1, and that's so. Therefore, this is precisely if we know that this is the definition of ergodicity of one of the equivalent forms. That if the T invariant sets must be negligible, or they must have full measure. Here we have some characterization of weak mixing. And as I said, you see that this is that for each power p, this is equivalent to weak mixing. But what is important here, this property is very important because it allows us to show that weak mixing implies total ergodicity. If system is weak mixing, then every power of system is also weak mixing, and weak mixing by the previous proposition implies total ergodicity. So therefore, if every power is weak mixing, then every power is ergodic. So here, it's important that you have this convergence for every subset. Whenever n is outside set, depending on A and B, with zero upper density. Okay, and here we have another concept of weak mixing functions. And we say that the function L2 is weak mixing if this condition holds. If this converges to zero. And the space of all weak mixing functions, will be denoted by W9. And it turns out that the space of all weak mixing functions is invariant linear subspace of L2. So this is not obvious that this is linear subspace of L2. In order to show this, we have to use van der Kolk lemma. So I'll show you in a moment briefly how we can do this. We will omit many details today because I have much more than I'll be able, to discuss, even having been back-to-back lectures. But so what's important here? So if every function is weak mixing, then this implies this. So therefore, so in other words, if every function in this measure preserving system is weak mixing, then the system is weak mixing. Okay, so here we have a definition of weak mixing systems. So in particular, this holds for every f and g, for every g which is inverted. And okay, so let me show you how to prove how to prove this property. Okay. Of course, from this immediately we obtain that this is linear subspace of L2. We have this for every F and G, F from weakly mixing, and for every G from L2. But in order to see this, so we have to use van der Kolk lemma with this sequence. When we go back, van der Kolk lemma is here. You see, if we want to show that this, the norm of this is zero, we have to verify this condition. In fact, this condition for this sequence. Okay, so we need to show that this converges to zero with this choice of elements. So if we do this, if we put this UN and the definition of UN plus H, then we obtain this. Okay, and now, so what do? We apply okay, so we apply Cauchy-Schwarz here for this expression. And then we use translation invariance. A little bit confused by.
I think you have two Cauchy-Schwarz inequalities, like for the first two inner products, and for the third one we use the invariant.
Yeah, that's right. Okay, so that's right. Yes. So this is, yeah. Okay, so for instance, we can apply Cauchy-Schwarz for this and for this to obtain this, and then here we can apply we exchange the order of summation, and then we apply T invariance. The measure mu is T invariance, so to remove this dependence of n. And then we don't have dependence of n anymore. We have just sum over h. And the fact that this, what we have here, is f is weakly mixing function, so by this condition means that this limit is 0 here, so therefore everything converges to 0. So therefore, by the van der Korpel lemma, so we have shown this. Yes, we verified this condition for this sequence. So by the van der Korpel, we know that this converges to 0 in alpha norm. And now, if we pair this guy with function g and use dominated convergence theorem, then we deduce that this holds with power 2 here, and we are done. And here you see that, so this is with power 1, but this is equivalent. So in one direction by Cauchy-Schwarz, in the other direction by the nestedness of little LP spaces. So therefore, so if we have this convergence with L2 norm, then we also have this convergence. Here, in fact, we apply Cauchy-Schwarz, so we can L1 norm can be replaced with L2 norm. For L2 norm, we have this, then we are done. So therefore, this is how we got this. And now we can use this condition to prove that our space is closed under. So it's clear that it's closed under multiplication by scalar. What we have to show, we have to use this to show that T is closed under addition. But now having this condition, then we see that if we take two functions from Wn which satisfy this condition, then by linearity or bilinearity scalar product, using this, we can use that this is closed under conditions. And the fact that this is closed, then this is simple argument, right? We take sequence like convergence. So we see that all sequence. This is by, in fact, consequence of Cauchy-Schwarz that the closeness of this space, and T invariant is also because we underline measure mu is T invariant. So it's clear. Okay, so therefore we see that this space of weakly mixing functions is a subspace, closed subspace of L2. This will be very, very important. And now, yeah. Okay. So this is the consequence of this theorem. The measure preserving system is weak mixing if and only if every function with mean 0 is mixed. So we have to do this mean 0 because we want to make sure that convergence is to 0. And okay, maybe I'll skip this. This is fairly clear that something like this must be true having this condition, this proposition. So let's go further. And here I would like to present a very deep theorem that we prove only in the bilinear case. But you see here, in fact, when Christenberg proved his result about Semereni, so he considered this averages. These averages correspond to, so this is in fact, I think that this is the scalar product of certain multilinear average where each function, where we have characteristic function of E, and the first is composed with T to power n, the second is composed with T to 2n, and so on. K is composed with T to K. So this is, in other words, multilinear ergodic average. And Christenberg, to deduce this, he established, the positivity of this live-in. So therefore, this is in some sense, the weakest possible asymptotic behavior of this. But there was a question, what is the really asymptotic behavior of these averages, especially, in historically it was motivated by von Neumann and theorem and Berkhoff, where for linear averages we know that we have pointwise almost everywhere, non-convergence in the linear setting, but in the multilinear, this theorem was a trigger to ask what is the asymptotic behavior of the multilinear averages like here. Okay, so you see that if we take a character fj is a characteristic function of E, then this average corresponds with average that arises in first degree. And there was a question what happened with the limit. So that was the starting point of big programs to understand what happened with the limiting behavior of this. And so here so this is L2 limit was understood at the beginning of it was I think in 2002 by Host and Kram, and then independently by Tamar Ziegler. Very big work where the characteristic factors were understood in the context of this. Characteristic factors are certain T-invariant subspaces. So in this lecture, I wanted, to, in the context of Roth theorem, one can avoid, using characteristic factors. One can rely only on functional analytic language, and this is what I did in this lecture. Yeah, I'm quite proud that it was possible to present it in this way. But I know that this is not. I don't claim that this is the approach. It's not, but we don't need to introduce, this definition of characteristic factors, which are understood, in the context of this theorem. So, but if you ask, about pointwise almost everywhere convergence, for this is widely open, even for averaging operators for k equal 3. So this is one of the major open problems in ergodic theory and harmonic analysis. So attracts attention of many people. And yeah, so we believe that this is true. Pointwise convergence is true, but it's really, really hard. Only the bilinear case, it's the famous result of double recurrence, almost everywhere double recurrence theorem of Dugan from the early 1990s, where he proved this convergence in 4K. So in other words, almost everywhere convergence on the context of Roth was established. But yeah, other than that, we don't know. It's open, and it seems that it's very, very hard. But today we don't touch pointwise convergence at all. So we only talk about non-convergence, and I would like to show you how this can be established by the normal established in the context of bilinear operator whenever k is equal to. So the bilinear operator corresponds to the Roth. And so here we have the first simple instance, and here you can appreciate how important weakly mixing concept is to find a limit for L2. So it turns out that if one function, at least one, let's assume that our functions are bounded. If at least one function is weakly mixing, then we have convergence in L2 to 0 of this averaging operator. Okay. So, and as you can imagine, this is again the main tool here will be van der Korthout lemma, which will be applied, to this sequence of vectors in sequence. Of course, we can assume that this is in L infinity because we work with probabilistic measure preserving system, and infinity is probably n LP space. So, so here we have. So here is the proof. We have to verify this condition in the van der Korthout. We have to show that. You remember average, the lim sup of the average of the expressions of this form converges to 0 and goes to infinity. So let's take a look what is this. Okay, so if we apply un here and in place of n plus h, and by the definition, this is this integral. So here's this corresponds to the first vector here, this corresponds to the second vector. And now this is what we do here. We pair. Okay, first of all, we see that everywhere here we have n. So therefore, 1 power of t of n can be pulled out, and we can use the translation, the t invariance of measure mu. So therefore, this can be removed, and therefore we obtain this and this. Okay, so now. So if we average over n and pass with capital N to infinity, then so we can insert this. So this guy, the good thing about this part is that it's independent of n. So therefore it can be, so we can put the average here on this perspective, and we can use polynomial ergodic theorem and ergodicity. So here is important that we work with weakly mixing systems, because weak mixing implies ergodicity. So therefore, and we know that polynomial theorem for ergodic systems converges to a constant, which is an integral. So therefore, this guy converges to the integral of this, because here this system is ergodic here. And so that's a good thing. So therefore, you see that we were able to. So here we put some, some kind of. So here we see that this is another place which shows that ergodic theorems are some kind of asymptotic Pythagorean theorems. Here we see that this, and we know why this limiting by passing to averaging and passing to the limits we were able to put this converges to the product. So this is some kind of orthogonality. And yeah, so here, so therefore we prove this, okay? We prove this now. And now we see that if at least one function here is weakly mixing, if we average over h now and pass and use Cauchy-Schwarz and pass with h to infinity, then this converges to 0. So therefore, here by the von der Korput lemma, we obtain that this limit is equal to this limit, and this is 0. So, and that's how the proof goes for post-Graf-Ziegler theorem for weakly mixing functions. And in fact, here we use this fact that if f is weakly mixing, then any power of this function is weakly mixing. This is what follows from this characterization of weak mixing. So we have this nice theorem, and as you can imagine, in order to prove this, to prove that the limit exists, if we have for weak mixing, and we know that the space of weak mixing function is a closed subset of L2. So therefore, we have to understand what happened on the orthogonal compound. So this is another instance, how we that we proceed, by this. Another instance where this Pythagorean kind of argument is very useful. So, okay, so here we have to understand what happens, with this averages on the orthogonal compound with the mixing functions. And the orthogonal component, of course, makes sense because this is closed subset of O2. So therefore, we know that it exists, but we would like to have a more precise description of this. And here, this description is available, and so for this purpose, we have to introduce two new concepts. So the first concept is we consider the space Ex. This is the span of all LG functions, which are eigen functions for the Kopman operator for certain lambda from the torus. Well, this is unitary operator, so therefore all eigenvalues lie on the torus. They have length 1. And the other concept is the concept of compact functions or almost periodic functions. So we say that the function f is compact almost periodic if the closure of this orbit in L2 is a compact subset of L2 with this strong topology. So in this space will be denoted by this. Okay. And now what is very important here, it turns out that the orthogonal complement to weakly mixing function, this is the space of all almost periodic functions. And on the other hand, almost periodic functions, in fact, coincides with the space of all eigen functions. And so, so therefore, we will have this decomposition. So with this decomposition now, you see that we verified Poskra-Ziegler theorem for weakly mixing functions, and this is what now we have to understand is reduced to understand limiting behavior of this bilinear form for eigenvectors of the Kopman operator. This operator here, and this can be done in a fairly simple way. But so here we have. So here is the proof which shows that this set is orthogonal to this set of compact almost periodic functions is orthogonal to this set. Maybe I'll skip this. This is just a technical thing. The other thing is we have to show that the orthogonal complement of this is contained in the space of weakly mixing functions. If we do this things, and this inclusion requires some work. So it's based on some basic theory of Hilbert-Schmidt operators. We use the fact that Hilbert-Schmidt operators are compact, and this requires some amount of work. So it's not yeah. So but maybe this is technical thing. Maybe I will skip this. And so this is what we do. Here we have also a lemma which shows that almost periodic functions are closely invariant subset of O2. This is also very simple thing. And so this is what I want to show you. This will be this decomposition having all these properties and that we gathered. And this decomposition is called the Jacobs-Licksberg decomposition. Very important decomposition in ergodic theory, and also in operator theory for theory of Markov operators. So this can be derived in a much more general context. But here we work with Hilbert spaces, so it's more than enough. But it turns out that for theory of positive Markov operator, this is also available and now it's exploited in my context. Okay, maybe I'll stop here. We make a short break.
Any questions for the first one? Okay, if not, then let's make a 10-minute break until 5 before 12.
Yeah.